Okay, here we are on page 9 of trig equations and identities. So first of all, let's review some of these trig relationships. Sine squared plus cosine squared is the Pythagorean identity. It's equal to 1 squared or 1. Why is that? Because on the unit circle, if you take any point on the unit circle, remember that the coordinates are cosine theta, sine theta, right? So if I have a little triangle, cosine theta, sine theta would be the legs of this right triangle. And if these are the legs of the right triangle, couldn't I square each one, add them together, and I would get the hypotenuse squared? And remember, the hypotenuse of a unit circle is 1. So sine squared theta plus cosine squared theta is always equal to 1. Sine theta divided by cosine theta, that, remember, is tan theta. And 1 minus cosine squared theta, that's just a rearranged version of this. If I subtracted cosine squared theta from both sides, minus cosine squared theta minus cosine squared theta, wouldn't I have sine squared theta by itself on one side, and I would have 1 minus cosine squared theta on the other side? By the way, I could also have the opposite. I could have this, right? So when you see 1 minus cosine squared theta or 1 minus sine squared theta, think, oh yeah, it's a rearranged version of the Pythagorean identity. Okay, so let's do some simplifications. Sine theta plus sine theta, that would be equal to 2 sine theta. C would be 3 sine theta minus sine theta is equal to 3 sine theta minus 1 sine theta, so that would be 2 sine theta also. Tan theta minus 3 tan theta, that's 1 tan theta minus 3 tan theta, so that's equal to negative 2 tan theta. 2a, if I have 3 sine squared plus 3 cosine squared, I could factor out the 3, and I would have in the inside the Pythagorean identity, so that's equal to 3 times 1, or 3, right? If I have minus cosine squared minus sine squared, I could factor out a negative 1 from both, and then I would have cosine squared theta plus sine squared theta equals negative 1 times 1, Pythagorean identity here again, so negative 1. 4 minus 4 cosine squared theta. This doesn't look familiar, but first I'm going to factor out the 4. Then I would have 1 minus 1 cosine squared theta left. Oh, 1 minus cosine squared theta, that is this here, right? So I could replace this with sine squared theta. So this is equal to 4 sine squared theta. Cosine squared theta minus 1. Ooh, this looks suspicious too. So one thing you can do if you don't want to think about this backwards is I could replace the 1 with sine squared plus cosine squared, and then I would eventually get it. Okay, we'll do that in a second. But first of all, I'm just going to say, oh, this looks a lot like this. It's just the opposite. So I'm going to factor out a negative 1, and I would end up with negative cosine squared theta plus 1. And now the inside does look like this, and I can replace with sine squared theta. And then I could just multiply the two together, and I get negative 1 sine squared theta, right? Another thing I could do, like I said, was I could replace this with the Pythagorean identity. So that would be equal to cosine squared theta minus sine squared theta plus cosine squared theta. So I would distribute the negative sign to each one, and I would have cosine squared minus sine squared theta minus cosine squared theta, and you can see I would end up with negative cosine squared theta also, okay? What if I factored out the 2 here? It's a common factor. You can see there's a pattern here. Factoring out common factors often helps us see what we need. Oh, cosine squared minus 1. Again, it's the opposite of what we have here, so we'll factor out a negative from there also, and that would give us this, negative cosine squared theta plus 1. Now we have exactly what we have up here, so the inside is sine squared theta, negative 2 sine squared theta. Okay, here the top is sine squared theta, and the bottom is sine theta. And so sine squared theta on top, sine on the bottom, that leaves sine theta on the bottom, because remember the top is sine theta minus sine theta times sine theta, the bottom is sine theta. So when you cancel out, sine theta on top, sine theta on the bottom. You end up with just 1 sine theta. Number 3, so I have 3 tan x minus sine x cosine x. Remember, sine x cosine x is equal to tan x. So now I have 3 tan x minus tan x. So that would be the same as 3 tan x minus 1 tan x. So that would be 2 tan x. Tan x times cosine x. Remember, tan x is equal to sine x divided by cosine x. So I could cancel out the cosine x and end up with just sine x. This one too, I could substitute in sine x cosine x, sine x over cosine x for tan x, and then I would have 3 sine x plus 2 cosine x times sine x divided by cosine x. The cosines would cancel, and I would end up with 3 sine x plus 2 sine x equals 5 sine x. Expand and simplify if possible. Remember, when you have parentheses and two things added together and a squared, you need to do FOIL. So this would be 1 plus sine theta plus sine squared theta. So the middle would be 2 sine theta plus sine squared theta, right? Okay. Remember the identity a plus b squared equals a squared plus 2ab plus b squared. Maybe you might have that memorized for vestibular or for SAT. Same thing here. We could use this identity again. Tangent squared alpha minus 2 tangent alpha plus 1. How did I do that? I just did FOIL. So first I multiplied the tan alphas together and got that. I multiplied the negative 1s together, I got that. And then I multiply the negative 1 times tan theta, tan alpha, and I multiply those two together. I get negative 1 tan alpha twice. So then that would be a negative 2 tan alpha. I do FOIL for these. I'm going to square sine beta, so I get sine squared beta. I'm going to square negative cosine beta. That would give me plus cosine squared beta. And in the middle, I'm going to have negative 2 sine beta cosine beta. Why does that happen? Because remember, the middle term is 2 times a times b. 2 times a times b would be negative 2 sine beta cosine beta. All right. Expand and simplify sine x plus tan x and sine x minus tan x. Okay, so first I'll just do this without knowing the identity, which is a minus b times a plus b is actually equal to a squared minus b squared. Okay, first I'm just going to use FOIL. So I'm going to multiply these two together, I'm going to multiply these two together, and then I'm going to do the inside and the outside. So sine squared x is the first term. The last term is tangent squared x with a negative sign, right? Now if I multiply these two together, it would be sine tan. If I multiply these two together, it would be negative sine tan. I would have sine tan, and I would have negative sine tan. And now you can see that these two would cancel each other out, and you're left with just sine squared x minus tangent squared x, which is a famous identity, this identity here. Okay, factorize. So if I'm going to factor this, remember this is a famous identity. It's a squared minus b squared. So it's 1 squared minus sine squared theta. So this is equal to 1 minus sine theta and 1 plus sine theta. Because remember, a squared minus b squared is equal to a famous identity. It's a minus b times a plus b. Okay, and that's what I did here. Same thing here. This is equal to tan squared alpha minus 1 squared. So this is equal to this again. Tan alpha minus 1, tan alpha plus 1. Okay. This one is something different, apparently. Let's factor out the cosine phi because that's a common factor. We'll end up with 2 plus 3, 2 plus 3 cosine phi. Cosine phi times parentheses 2 plus 3 cosine phi. I don't think there's anything else we can do with that. We're done. They just said to factorize. We factorized. We factored out the common factor. Oh, so this one, remember these? So now what we need to do is say, okay, we've got a quadratic here. This is pretty hard to do without substituting some stuff. So let's change our tangent thetas into x so it looks something more familiar. So tangent squared theta becomes x squared. Tangent theta becomes x, and 6 is 6. Oh, now we can factor this. Right? So now we'll just replace the x's back with tan theta. So that would be tan theta plus 3 and tan theta plus 2. And we're done. Same thing with these, right? It's a little bit easier if we replace our cosine alpha with x, and then we would have 6x squared minus x minus 1. This is already a hard factorization problem as it is with the 6 here. So how do we factor this? Okay, I'm just going to do factoring of this problem, which has a equals 6, which is not one of the easiest, but let's see. The candidates for factoring 6 are 6 and 1 and 3 and 2, right? The candidates for factoring 1 are 1 and 1. Okay, so now what we're going to do is we're going to try to find which of these pairs is going to give us a sum or a difference that's 1. Okay, so first we'll try 6x and 1 and 1x and 1. Is there any combination which, no, it's not, right? Because we're going to have 6 and 1. If we add them, it's going to be 7. If we subtract them, it's going to be 5. So it's not 6 and 1. It has to be 3 and 2. So let's write down 3 and 2. So 3x and 1 or 2x and 1. Now this is promising, right? If I multiply 1 times 2, that's 2. If I multiply 1 times 3, that's 3. The difference between the two is 1. So this looks like it's going to be it. Now, it could be plus minus, or it could be minus plus, because when I multiply the ones together, I should get a negative. So there has to be one negative, one positive. Oops, I did it a little bit wrong there, didn't I? They have to be different. Okay, so it's either going to be plus minus or minus plus. Which is it? So if I multiply the 3 times negative 1, then that would be negative 3 plus 2, and that would be negative 1. So I think it's this one, okay, this pair. All right, so let's write down the final factorization. 3x plus 1 times 2x minus 1. Just to make sure everything's okay, let's actually multiply the insides and the outsides. So we'll get 2x minus 3x, and that'll give us negative 1x. So yes, it works. Okay, now that we have the factorization, we can put the cosine back in, right? So we're going to put 3 cosine alpha plus 1 and 2 cosine alpha minus 1. So we're done factoring. Now, remember how I told you never have to do factoring in this class? So if you were going to do this using quadratic formula, how would you do that? You would put in your a value, your b value, and your c value into negative b plus or minus square root, blah, blah, blah. And then you would end up with x equals negative 1/3 and 1/2. You get those two numbers. And so then you would say, okay, if I want to factor this, then I would just put x plus 1/3 and x minus 1/2, because that would be the factored binomials that would yield these two solutions, right? And then I would put a leading 6 because the a value is 6. All right, page 10. Simplify 1 minus sine squared over 1 minus sine. Remember, this top is a famous identity. 1 minus sine alpha and 1 plus sine alpha on top. 1 minus sine alpha on the bottom. Look at these cancel, right? This cancels with this. So I am left with 1 plus sine alpha only. Oh, here's the famous identity again. So the top is going to become cosine phi minus sine phi, and then cosine phi plus sine phi on top. And the bottom is going to be cosine phi plus sine phi on the bottom. And the bottom is obviously going to cancel with the right side. And so we're left with cosine phi minus sine phi over 1. Okay, and on this one, so this one, we have the famous identity on the bottom. So the top is going to be just what it is, and the bottom is going to be sine alpha minus cosine alpha times sine alpha plus cosine alpha. And so these two are going to cancel, and then we're left with 1 over sine alpha minus cosine alpha. Okay. Show that this simplifies to 2. Okay, so remember that this is a FOIL, a squared plus 2ab plus b squared, and this would be a squared minus 2ab plus b squared. So we're going to put cosine squared theta plus 2 sine theta cosine theta plus sine squared theta. So that was the first one. The second one would be cosine squared theta minus 2ab, no, not 2ab, 2 sine theta cosine theta plus sine squared theta. So let's cancel out this and this. You have a positive and a negative version of each other, and then we can add these two together, and we add these two together, and we just end up with cosine squared theta times 2 plus 2 times sine squared theta. If we factor out the 2, we end up with the Pythagorean identity here. 2 times 1 is 2. We're done. Okay? Q, E, D. 1 minus cosine theta times 1 plus 1 over cosine theta simplifies to tangent theta sine theta. So let's show that this is true. So most obvious thing to do is we can expand this. We can do FOIL. So first we're going to do these two together, and then we're going to do these two together. So it'll be 1 squared, and then negative cosine theta over cosine theta. Okay, and then we're going to do these two together and these two together. So that would be plus 1 over cosine theta, negative cosine theta. Cosine theta over cosine theta is 1, of course, so this is equal to 1. 1 squared is 1, of course, so 1 squared minus 1 is just 0. Then I'm left with 1 plus cosine theta minus cosine theta. How is that going to become tan theta times sine theta? Not sure, but we do need sine somehow. Well, we obviously need to combine these two into one term because that's the way this is. How do we add things that, are fractions? We need to get a common denominator, right? So let's make a common denominator for the second one. We'd have to multiply both the top and the bottom by cosine theta. And then we would end up with 1 over cosine theta minus cosine squared theta over cosine theta. And then we would combine the tops and leave the bottom as a one denominator. Oh, and now we see it. 1 minus cosine squared theta, that's that identity from before, that's sine squared theta, right? So sine squared theta on top, cosine theta on the bottom. Now we're getting close. We can take sine theta and make it into 2 sine thetas multiplied together. And then we group together these two as tan theta, and then we end up with tan theta sine theta. Okay? All right. E. Again, if you have two fractions that don't have a common denominator, what you want to do is you want to get a common denominator. So let's multiply the first one times sine theta over sine theta. because that is going to get us a common denominator. And the second one will also multiply by 1 plus cosine theta, because that will also get us a common denominator. So let's see. So the denominator is perfect. Sine theta 1 plus cosine theta. That is a common denominator. The first term becomes sine squared theta. The second term becomes, the identity, right? So 1 squared plus 2 cosine theta plus cosine squared theta. Oh, and then look, I have sine squared theta and cosine squared theta on top. That simplifies to 1, right? So now I have 1 here, I have 1 here, so that would be 2 plus 2 cosine theta. The bottom, I have sine theta times 1 plus cosine theta. You can see that the top, you can factor out a 2 now. 2 factor out of 1 cosine theta on top, sine theta 1 plus cosine theta on the bottom. These two cancel. I end up with 2 over sine theta. Is that what yeah, that's what I wanted. Last one. Once again, we have two fractions. We need to add them together. We're going to multiply them times a common, something to make a common denominator, right? I'm going to do the multiplications in a different color so that maybe it's easier to follow. Okay, so that's the original question. Now I'm going to multiply by something that would give both a common denominator, right? Now the bottom is a common denominator. It would be 1 plus sine times 1 minus sine. I abbreviated by not writing the thetas for now. The first term would be 1 plus sine theta because it's just multiplied times 1. And the second one would be 1 minus sine theta. So now I can see that I could combine these two and get 2. I could combine these two and get 0. So I'm going to have 2 on top. And the bottom is going to be 1 minus sine squared theta because it's the identity, right? 1 squared minus sine squared theta. 1 minus sine squared theta, that's the same thing as cosine squared, right? Right? 1 minus sine squared theta equals cosine squared theta. 1 minus cosine squared theta is equal to sine squared theta. Okay. All right, and that's what we wanted. Double angle formulas. Remember from our investigation that sine 2 theta is equal to 2 sine theta cosine theta. Cosine 2 theta has 3 possible combinations. This is one. This is another. And this is another. So how do you know? Oops. Let me just rewrite that. 2 sine squared theta. How do you know which one to use? You're going to use the one that is the least complex. You don't want to add more sines and cosines to what you already have. If you already have sines in your expression, try to use this one. If you already have cosine squared in your expression, try to use this one. Don't add sines if you only have cosines. Don't add cosines if you only have sines. Okay? All right. Number 1, if sine theta equals 4/5 and cosine theta is 3/5, find the exact values of sine 2 theta and tangent 2 theta. Well, first of all, sine 2 theta, remember, is 2 sine theta cosine theta. So all we need to do is plug those in. 2 times 4/5 times 3/5 equals, multiply the numerators together, that would be 2 times 12 is 24 on top. The bottom is 5 times 5, it's 25. That's it. What about tangent 2 theta? Tangent 2 theta, there's a couple ways you can do this. One is you could draw a triangle and figure out what tangent value would would occur with the sine of 24 over 25, but I think it's easier just to use the identities. Tangent of theta, remember, is equal to sine 2 theta over cosine 2 theta. And we already have sine 2 theta. So we have sine 2 theta from here, 24 over 25. Let's find cosine 2 theta using any of these three identities. You can see that we have both sine theta equals 4/5 and cosine theta equals 3/5. So we could fill in any one of these and it would be fine, right? So let's use cosine squared minus sine squared, just to variar. Let's see. We very rarely have a chance to use this because since it demands that you know both, it's like whenever you can use this one, you can use either of the other ones, right? So cosine squared theta would be 3/5 squared, and sine squared theta would be 4/5 squared. So let's write 3/5 squared for cosine squared theta, and then sine squared theta would be 4/5 squared. And so 3/5 squared would be 3 times 3 on top, 5 times 5 on the bottom. 4/5 squared would be 4 times 4 on top, 16, 25 on the bottom. So 9 25ths minus 16 25ths would be negative 7 25ths. And then if I fill in sine 2 theta and cosine 2 theta, I would have 24 over 25 on top, and I would have negative 7 over 25 on the bottom. And the 25s cancel out, and then we're left with negative 24 over 7. Just to review about why the 25s cancel out, I'm just going to write it out here. If I have 24 25ths divided by negative 7 25ths, remember that this is the same thing as multiplying by the inverse. So I inverted this, and I'm multiplying now. And now the 25s obviously cancel out, and then I'm left with negative 24, because there's a negative here, over 7. If cosine A is 1/3, find cosine 2A. Okay, so in this case, we're going to use one of these three equations. We only know cosine A, so why would we use any of these except for this one? This one's the best one because it only has cosine in it, right? So you can see it's not that hard to figure out which one you're supposed to use. So 2 times 1/3 squared minus 1 equals 2 times 1/9 minus 1, 2/9 minus 9/9, because 1 is 9/9, is negative 7/9. Okay. Last one. If sine alpha is negative 2/3, where alpha is between pi and 3 pi, remember pi is 90 degrees, and 3/5 pi is 270 degrees, find the exact value of cosine alpha and sine 2 alpha. Okay, so if sine of alpha is negative 2/3 and it's between 90 and 270, oh, I'm sorry, not 90 and 270, it's 180 and 270, right? So it's in the third quadrant. So that would be like this triangle right here, right? This triangle right here. So the sine is negative 2/3. So that means the y coordinate is negative 2/3, the hypotenuse is 1. We want to know what this is. We could use Pythagorean's theorem, right? The Pythagorean theorem for this triangle would be, let's call this x, so it would be x squared plus negative 2/3 squared equals 1 squared. So that would be x squared plus 4/9 equals 1, x squared equals 5/9, x equals square root of 5 over 3. Okay, and is it a positive value or a negative value? Well, the x value is going backwards, so it would be a negative square root of 5 over 3. Okay, so cosine is equal to negative square root of 5 over 3. When I took the square root, I need to put plus or minus, right? But in this case, I know that the cosine value is negative from the drawing, so that's why I know that this should be negative square root of 5 over 3. All right, now that I have the cosine value and I have the original sine value, it's pretty easy to find sine 2 alpha because sine 2 alpha is 2 sine alpha cosine alpha. So it's equal to 2 times negative 2/3 times negative square root of 5 over 3, which is equal to 2 times 2 times square root of 5 over 9, which is 4 square root of 5 divided by 9. What happened to the negatives? They cancel each other out. Done.